Welcome to The Explainer. I am absolutely thrilled you're tuning in today because we're going to completely master linear geometry together. Whether you're a student trying to ace your next math exam, or honestly, just someone who loves understanding the hidden structure of the world around us, this step-by-step lesson is designed right for you. We are going to unpack some incredibly powerful mathematical concepts today. We'll start with the absolute foundational basics and then build all the way up to some really cool, practical, real-world applications.
So let's kick things off with a question that, well, it might seem pretty simple at first glance. Can visual appearance alone guarantee the relationship between two lines? I mean, we've all looked at a graph or a quick sketch and thought, oh yeah, those lines look parallel, or that definitely looks like a right angle. But here's the truth of it. We literally cannot just eyeball a graph to know for sure. In mathematics, a drawing might strongly suggest a relationship, but it doesn't guarantee a single thing. Math requires proof. It requires strict conditions to be met, and today we're going to learn exactly what those conditions are.
Here's our roadmap for the lesson. First, the anatomy of a line. Second, guarantees of parallel lines. Third, guarantees of perpendicular lines. Fourth, real-world linear applications. And finally, a quick lesson recap and takeaways. Let's get right into it.
Okay, part 1, the anatomy of a line. Before we can even begin to understand how lines interact with each other, we have to know what makes a linear function in the first place. The whole secret is locked inside this simple but super powerful equation, y equals mx plus b. This defines a linear function. The absolutely crucial, defining feature here is that the highest exponent on our variables is just 1. That's called its degree, and a degree of 1 guarantees a perfectly straight line on a graph. Let's break this down just a bit more. The x is our independent variable. That's the input. It's the thing we can actually control or change. The y is the dependent variable. It's the output, or the final result that depends entirely on whatever happens to x.
To truly grasp this, let's look closer at the m and the b in our equation. Think of the slope, the m, as the steepness of a hill you're climbing. It basically tells you your rise over run, exactly how far up or down you go for every single step forward. On the flip side, think of the y-intercept, the b, as the literal starting line of your race on the y-axis. It is the exact point where your line crosses that vertical axis, precisely at the coordinate 0, b.
Let's actually look at this in action with our very first test case, the equation y equals x. Notice that straight line crossing right through the origin at 0, 0. Because the highest exponent here is a hidden 1 right there on the x, it passes the linear test perfectly. And because our slope, our m, is positive, you can clearly see the line slanting upward as it moves from left to right.
But what happens if we mess with that hidden 1? Take a look at this equation, y equals x squared. Look at what happened to our nice straight line. It formed a curve, specifically a parabola. Why? Well, because the exponent on the x is now a 2. The degree is greater than 1, so this completely 100% fails the linear test. It is not a linear function.
Now coming back to our linear rules, take a look at this one, y equals negative x plus 1. The degree is back to 1, so boom, we have a straight line again. But notice the direction this time. It slants downward from left to right. That's because our slope, our m, is negative. And notice where it crosses that vertical y-axis? Right at positive 1. That's our y-intercept. That's our starting line.
So the really empowering thing here is that you now have the tools to graph any basic algebraic linear equation yourself, using just 2 simple steps. Step 1, you plot your y-intercept, your b. Just find that number on the vertical axis and draw a dot. Simple as that. Step 2, from that dot, use your slope, the m, as a set of literal directions. If the slope is 3, well, that really means 3 over 1. So you rise up 3 units, you run to the right 1 unit, and you plot your second dot. Connect them, and look at that. You've just graphed a line.
Moving on to Section 2, Guarantees of Parallel Lines.
Now that we know how to build a single line, let's see how 2 different lines interact. First, we've got to understand mathematical planes. Coplanar lines lie on the exact same flat surface, or plane, extending infinitely. What does coplanar actually mean in plain language? Well, imagine you're standing in a room. If you draw 2 lines on the exact same wall, those lines are coplanar. But what if you draw one line on the wall and another line way up on the ceiling? Those lines are on completely different planes. They're non-coplanar. And if they're on different planes and never touch, math calls them skew lines. Basically, they're like 2 roommates actively ignoring each other on totally different floors of a house. And this brings us to the formal definition of parallel lines. They are straight lines that are always exactly the same distance apart and never intersect. But here is the major catch. Being coplanar isn't enough on its own. You can draw two lines on that exact same wall we just talked about, and they might still cross each other like a giant X. To be truly parallel, they must be coplanar, and they must never ever intersect, no matter how infinitely far you extend them.
So, jumping back to our earlier question, how do we guarantee this mathematically without just trusting our completely unreliable eyes? Here's the algebraic guarantee right here. Equal slopes. If you have two distinct non-vertical lines and you calculate their slopes, and the slope of line 1 is exactly equal to the slope of line 2, meaning m1 equals m2, they are mathematically guaranteed to be parallel. Their steepness is identical, so there is simply no way they will ever catch up to each other.
And just to give you the whole shebang, there are geometric guarantees too. If you draw a straight line, called a transversal, cutting right across two other lines, it creates pairs of angles. If those specific angle pairs are congruent, which just means they have the exact same measurement, that is an absolute mathematical guarantee of parallelism. This includes congruent corresponding angles, alternate interior angles, or alternate exterior angles. If any of those match up perfectly, your lines are parallel. No questions asked.
All right, Section 3, Guarantees of Perpendicular Lines.
So what happens when lines actually do cross, but they do it in a very specific, incredibly strict way? Welcome to the realm of perpendicular lines. By definition, these are two intersecting lines that form a perfect 90-degree angle, otherwise known as a right angle. Visually, on a diagram, again, you can't just guess. You really need to look for that little square 90-degree box symbol tucked right into the corner of the intersection. That symbol is your guarantee. And what's really cool is that if just one of those four intersection angles is 90 degrees, math dictates that all four angles around that intersection must be exactly 90 degrees.
But what if you don't have the visual? What if you only have the algebra? What is the algebraic guarantee for perpendicular lines? Okay, it's a very complex-sounding term. Negative reciprocal slopes. Sounds intimidating, right? But let's break it down because it's actually super simple. It just means you take the slope of your first line, flip the fraction upside down, and give it the opposite sign. So if your first line is climbing a hill with a slope of 2, which, remember, is just a fraction of 2 over 1, the perpendicular line must have the opposite sign, so it becomes negative, and you flip the fraction, making it negative 1 over 2. If m1 is 2 and m2 is negative 1/2, they are guaranteed to cross at a perfect 90-degree angle.
Section 4, Real-World Linear Applications.
Okay, it is time to zoom out from the abstract algebra for a second and look at why this actually matters in real life. Linear functions are literally everywhere in the wild. They turn all these equations we just learned into actual financial tools. We see them in hourly part-time job wages, where your pay increases steadily over time. We see them in internet cafe fees, in mobile phone plans that charge by the minute, in mobile data top-up promos where you get a proportional data bonus, and even in food promos where a discount scales linearly with every single item you buy. Let's look at a really concrete example right out of the source material. Imagine you score a part-time job, and they're paying you 200 Philippine pesos per hour. How does that translate to y equals mx plus b? Well, your total earnings are the y. Your hourly rate, that 200, is your slope, your m, and the hours you work is your x. Because you start with 0 money before you clock in, your y-intercept, the b, is just 0. So the linear function modeling your paycheck is simply y equals 200x. Every single hour you move to the right on the x-axis, your bank account rises by exactly 200 on the y-axis.
Let's level this up to a slightly more advanced real-world model where your starting point, your b, isn't 0. Consider a delivery service. They charge a fixed base fee just for showing up, plus a scaling rate per kilometer. Let's say the base charge is 60 pesos, and the rate is 30 pesos per kilometer. That 60 peso fixed charge, that is your y-intercept. It's what you pay at exactly 0 kilometers. The 30 pesos per kilometer is your slope, the steepness of the cost. So the final cost of any delivery can be perfectly mapped out with the function y equals 30x plus 60.
And finally, Section 5, Lesson Recap and Takeaways. I really want to congratulate you on making it this far. You've covered a lot of ground. To cement this knowledge, I highly suggest you pause the explainer right here and take a screenshot for your study notes. Seriously, do it. This is your ultimate summary matrix comparing our two specific line relationships. Both must exist on the exact same plane, but parallel lines never intersect, guaranteed by having the exact same slope. Perpendicular lines, on the other hand, always intersect at 90 degrees, guaranteed by having negative reciprocal slopes. And you can clearly see the visual symbols for both of those right down here on the bottom row. We kicked this whole thing off by asking if visual appearance alone was enough, and we proved that math actually requires concrete guarantees, things like slopes and intercepts. But now I want to leave you with a completely different kind of question. Look at the real world around you. How can you use linear functions to calculate your own future part-time job earnings, or figure out the true cost of your next phone plan? You now have the mathematical tools to predict and track your own real-world success. You just have to apply the formula. Thanks so much for joining me on this explainer, and keep learning.